types of redox reactions are going to be completely new, completely different. You have to balance them based off of the moles of electrons, not based off of just regular elemental coefficients that you're used to doing. Now, we're only going to balance the ones in acidic solutions today. When we get to electrochemistry unit 6, we'll be doing the basic solution ones as well. But of course, a lot of these redox reactions form ions when they're exchanging electrons. That's why they're taking place in aqueous environment in solution. And we have this series of steps that we need to follow. And it does look daunting at first, but once you start working the steps, it's not as hard as you think. So, let's go ahead, start the first example here. What does step 1 say? We have to write out the separate half reactions, so let me show you how to identify those. Okay, you have two reactions. You have copper solid and you have nitrate ion. So, this is in an aqueous acidic solution. Okay, and you have two products. You have the copper 2 ion and you have nitrogen monoxide gas bubbling out of the solution. Okay, so when you're writing out the half reactions, you kind of have to do a little bit of reasoning here and say, okay, I have this reactant over here, what product could it possibly go to? And separate it out that way. So if I have copper solid right here, what's the only thing that we could probably match it with? Is the copper ion. Okay, so that would be our first half reaction. And I'm going to write the phases in at the end because it'll get very cumbersome if we do it the whole time. Now looking at the other one, of course, matching kind of the elements with the correct stuff. The nitrate obviously has the ability to create nitrogen monoxide. They both have kind of the same elements in there. And we want to make sure that we're writing it correctly there. Okay, so now that we have the two half reactions separated, we can start balancing them. All right. Now, what's the next step? What does it say? Balance anything that's not H or O. So, Cu is not H or O. We have one copper solid atom going to one copper 2 ion. Do we need to do anything with that? No, nice and balanced. Now over here, the nitrogen. There's one N in nitrate and one N in nitrogen monoxide. Do we need to do anything with that? No. Okay. What is the next step say? Balance oxygen with H2O. Okay, so on our left-hand side, the copper one doesn't have any oxygen in it, so we can ignore that one for now. Over here on the right, though, nitrate going to nitrogen monoxide, there's O's involved. Are they balanced? No, so we need to add in some water. So over here, we're going to add in some water. How many waters do we need to balance it? We need 2. So we're going to put 2 waters over there. Now by doing that, we have now messed up this particular reaction because we've added some H's in there. So what does it tell you to do next? Balance the H's. So if we put some H's over here, how many are we going to get? How many do we need to balance? 4 H's on this side. Okay, 4 H's. Now, the reason why we can add in water and add in H's freely is because it's already an acidic solution. So there's already water present, there's already H pluses present. So you can add them in when you need to use them because it's in an acidic solution. What does it say to do next? Balance the charge by adding in electrons. Well, if you look over here, copper solid is 0. Okay, this is 2 plus. So we need this side over here to add up to 0. So where are we going to put the electrons? And how many do we need? 2 electrons. Very good. Now, looking over here, do not do individual atoms in each particular compound. This is plus 4. Okay, so this is plus 4. This is minus 1. So this adds up to what? Plus 3. Over here we have a 0 and a 0, so this adds up to 0. So we have plus 3 to 0. How many electrons do we need to add in? 3. And where do we add them? Over here on the reactants. Good. Now, keep in mind, too, because it's redox, one thing being oxidized, one thing being reduced, the electrons should appear on opposite sides. So on our copper half reaction, the electrons are products. On our nitrate half reaction, the electrons are reactants. Okay, so they should be opposite each other. If you have them both on the same side, you know you've done something wrong. Now, what does it say to do? Does each half reaction have the same number of electrons? No. So how can we make them have the same number of electrons? We can go for the least common multiple, yes. So we're going to multiply this side by 3, but what you multiply the electrons by, you have to multiply all of the elements by. And on this side, what are we going to multiply by? 2. All right, so go ahead and do that. So we have 3 coppers going to 3 copper 2s plus 6 electrons. Over here, we have 8 hydrogens plus 2 nitrates plus 6 electrons going to 2 nitrogen monoxides plus 4 waters. Good. Now, since there's electrons on products and reactant sides that are equal, and that the electrons are now balanced, you get to cross them out. Okay? And now we just merge together. So you're going to merge all of the reactants together. Okay? 3Cu, and this would be a good time to add in your phases instead of rewriting them over and over again. But anything that's an ion, what are we going to put by it? AQ. And then over here, we're going to put all the products up here. So 3Cu2 plus AQ because it's an ion. 2 nitrogen monoxides, it did tell us up here it's a gas. And 4 waters, what are you going to label water as? Liquid. There you go. So that is the final balanced redox reaction. You have to balance the electrons. You can't just balance the coefficients of the individual elements or it will be incorrect. Now it's your turn to try on the next one. We'll come back and look at it in about 5 minutes. All right, let's separate, put our half reactions. So permanganate, MnO4 is obviously going to go to what?
Mn2 plus.
Mn2 plus. So that'll be our first half reaction. Oxalate's going to go to what?
Carbon dioxide.
Carbon dioxide, good. Okay. Starting off here. Now, got to balance our O's. So,
Well, wait, you gotta balance your C's.
we do have to balance our C's first. I'm going to change this a little bit so that I get more room. We got to balance our C's. So, what do we need to put here?
A
2. Good. Guess what that does for us?
2.
It also balances our O's, so that's nice. Yes, that worked out nicely. All right. On the other side here, just going to move this over a little bit, just so I have room. Now we need to add in some water. How many waters? 4 waters. Good. All right. So then that means over here we need to add in 8 H pluses. Very good. So far, so good. Now it's time to look at charge. Right? Time to look at charge. So this is -2. This is 0. So where do we need to add in our electrons? We need to add 2 electrons over here. Good. Now we have 8 pluses and a -1, so this is +7 on that side. On the right-hand side of it, we have Mn +2 and 0 from the water, so this is a +2. So that's a change of how many?
-5.
That's a change of 5. So we need to add in 5 over here. Okay? Now we need to balance our electrons because we have a 5-2 thing going on. So we need to go ahead and do least common multiple. This will be multiplied by 2. This one will be multiplied by 5. Okay? Multiply them out, cancel the electrons, and then merge. So this is what? 16 H plus 10 electrons. It's 2 permanganates going to 2 and then +2s and 8 waters. Alright, now on this side we have 5 oxalates going to 10 carbon dioxides plus 10 electrons.
Then you merge them.
Cancel out the electrons, then merge. So are all of our reactants, add in your phases at this point. Be a good time to do it. Going to our products, 2 Mn2 plus, ion gets AQ, 10 carbon dioxides
The gas.
is a gas, and we need our, I don't know what I just wrote there, but that's okay, we'll fix that. Gas plus the, what, 8 waters? Uh-oh. Why are we freaking out? There we go. All right. And we have our final merged answer. Okay? So this is the balancing in acidic solution arrangement. Okay? It is a lot of work. You should be able to easily recognize these guys because you have these weird ions and things usually in them. So you would have to separate and do the half reactions. It's not going to be like a standard single replacement looking type reaction. Yes?
So this is created from a net ionic equation because it kind of looks like a net ionic.
Yes. You're balancing it though. It's not really a net ionic equation because you need to have it balanced as well. You just have the building blocks of the equation to start with, and then you have to balance it based off of the moles of the electrons that are being transferred. So redox is all about the moles of the electrons. Okay? And that's kind of how the titration problems work. Alright, so here we're going to be looking at a titration problem where it's similar to the acid-base titration, where acid-base titration we had the H plus plus the OH-1 water. But here you have a certain amount of one of the reactants reacting with a certain amount of another of the reactant until that mole of transfer of electrons is equal. Okay, it's the same kind of idea. You're going to add in as much titrant as you need to analyze the analyte, okay, and figure out that amount. Now, the issue with redox titration problems is it usually has a big long paragraph, a lot to read, and it looks very intimidating. Okay, it's really not that bad though. So if you look here, potassium dichromate used to titrate a sample containing an unknown percentage of iron. The sample is dissolved in phosphoric and sulfuric mixture to reduce all of the iron to Fe plus 2. So the solid iron, they're reducing it so it gets into ion form, so it's in solution. Now that it's in solution, they can add stuff to it, react it with something else to figure out how much iron was in the original sample. Alright, so they just told us it's an acidic solution, okay? The solution is then titrated with this amount of potassium dichromate, producing iron and chromium ions in acidic solution. The titration requires 32.26 milliliters of potassium dichromate to do the entire sample size, which was 1.2765 grams. So we're going to determine the percent of the iron in the sample and then determine which type of iron compound is in the sample, okay, based off of that percentage. So let's start off with the basics here, determining the percent iron in the sample. Well, we have to start with our titrant, just like you would in a regular, neutralization type titration problem. It tells us that we have this many milliliters of this molarity, okay? And we're basically just going to work it to moles using our balanced reaction, okay? We want to know how much iron's in there, okay? So we have, the amount of iron here detectable, okay, based off of its mole ratio. So what I need to do here, first change my milliliters to what? Okay. Then I can do 1 liter equals 0.01625 moles of K2Cr2O7. Now the potassium really doesn't participate in the reaction because potassium is a what? Spectator, so we'll just take it out. So 1 mole of the potassium dichromate goes to 1 mole of dichromate, right? Now, from chromate, we can figure out how much iron it's reacting with. So, 1 mole of the chromate, dichromate, gives you 6 moles of your iron. Okay? So this is going to tell us how many moles of iron it reacted with, because this is how much it needed to be added till the color changed. The endpoint showed you when to stop, just like it would, you know, if it was an acid-base titration. There would be a color change, and you would know to stop. Okay? So what do we get for our moles here? And since we have 4 digits in each one, we want to keep 4 digits in our answer.
0.00314.
All right, so getting this as our moles. Yes, no, yes, no. All right. Now, that's the moles of the Fe, but in order to determine percent out of the sample, what do we need to change it to? Grams, right? So let's change it over to grams. So 1 mole Fe2 plus is going to equal what? 55.85 grams. Okay, so how many grams is that? Now, the iron out of our entire sample here, this is out of the sample size times 100. That should give us our percent. So our percent ends up being like 13.76%. See, it's not as bad as it seems, right? You just use the balanced reaction to figure out your information. But now that we know the percent, which it looks like we're good to go. Now we have to figure out, is it iron 2 phosphate, iron 2 iodate, or iron 2 acetate that's in the actual sample. So, basically what should we do here? Percent iron in each of those. Before I can find the percent iron in each of those, what do I need to know about each of those? Their molar masses, and so in order to find their molar masses, I need to know their formulas. So what's iron 2 phosphate? How do you write that?
Fe3. Fe3PO42.
Okay. Iron 2 iodate. What's iodate? IO3, right? IO4 is per iodate, okay, just so you know. And iron 2 acetate.
Fe2H3O22.
Okay, or you could write it like this, don't forget. Yes, it looks like that, I agree. Alright, so now we need to figure out the percent of the iron, you know, in this, you know, particular sample. Okay, so here you would do your 55.85 times 3 on the top, and then you need to add up all of it on the bottom. So I get 357.5 0.49 for this one, times 100, and that's going to give us fluid. This is what, 46.87%. So that's a what? No, right? Doesn't match. So it can't be that one. Let's look at the next one. So we have 55.85. Yes?
How did you get to 55.85 times 2?
Because there's 3 in the compound right there. Good question. Iodine is what, 126.9 times 2 plus 6 times 16 plus my iron. Are we getting 405.65? And this ends up being what? Oh, look at that, 13.77%. Might have a winner here. Now, let's just check. It's always good just to check. So over here, we have our, once again, 55.85 over what'd you get? 173 point what? 95. Are we in agreement? Sure. Everybody agree with that number? So this ends up being 32.11%. So yes, this one's definitely not a winner. So check, our substance is going to be iron 2 iodate. Now, your turn. Have fun. Figure them out. Stibnite that has antimony in it. Antimony being a metalloid on the staircase, don't forget. Alright, now, going over this one, we need to calculate the amount of antimony in the sample. So we have this time it's the bromate from potassium bromate reacting with our antimony. Sp3 plus here, okay, and it's gonna, oxidize it to Sp5 plus, and as you can see, the mole relationship is the same, but we are wanting to look at the titrant reacting with the analyte, so we're gonna stick over there on the reactant side, okay. So we have to move this over 1, 2, 3, change that to liters, okay. 1 liter equals 0.250 moles KBrO3. Now, sometimes the questions will ask you to go to moles. Sometimes it will ask you for just like the percent here. So, do we really need to stop at moles at this point? No, we can keep going. So, moles of KBrO3 equals 1 mole BrO3. Now I always write this step in here because it's not always 1-to-1, so you need to always make sure you write that in there. Now I can go from moles of bromate, 1 mole bromate, to 3 moles of Sb, and then 1 mole of Sb is going to give me how many grams of Sb? 121.76 grams Sb. Now, so when you calculate all that, what does it end up being? 1.995 is what? Grams. Okay, Sb. Over our total, which happens to be 9.62 grams times 100. So that ends up giving you 20.7%. This one only has 3 digits, so the percent should only have 3. But your mass still should have 4, just like these values right here, because those are your starting measured values. So yes, very good point to make. So here is the amount, here is the percentage, okay? Once again, they seem complicated, they're not as bad. Now that you've seen, really, it's just using stoichiometry in the balance reaction to figure out the info. Yes, question?
Referring to the SP3 plus or SP5 plus make a difference?
Not really, because as you can see, there the mole ratio is the same. It's
So
just an
will they
exchange of
always be-
electrons.
Will they always be balanced?
Well, the individual elements themselves for the electron exchange are usually balanced. Like in the previous problem, the iron was a 6 when it was +2, but it was also 6 moles of +3. So as you can see, usually those elements end up staying similar in terms of their moles, especially if they're elemental metals being oxidized.
So for notation purposes, would you always
But
do SP plus 3?
we would want to go with the reactants though, because the titrant is reacting with the analyte, and that's giving us the amount of the reactants. So for the idea of a titration, you have this much titrant reacting with this much analyte to get the exchange of electrons equal, and that's where we're figuring out the content from. But if you did work it to the products, you'd still get the same number. Okay? Good question.